Welcome to the Microsoft Fabric Machine Learning Lifecycle Success Strategy from Start to Finish, a four-part series. In a world where generative AI and tools like Copilot are transforming how we build, deploy, and consume intelligence, it's more important than ever to understand the foundations that make AI solutions reliable, scalable, and business ready. This series is designed to provide data professionals, business leaders, and machine learning engineers, moreover data scientists, a clear end-to-end blueprint, starting from framing a real business problem, like predicting real estate trends, all the way to operationalizing models with Microsoft Fabric. By the end, you will have a solid understanding of the full machine learning lifecycle and how to turn data into meaningful production-ready outcome or production-grade outcomes, right? If you are new here to our channel, welcome to the Data Significant YouTube channel, where real business use cases become practical, easy to apply data and AI lessons for our community. If you want content that's relevant, actionable, and grounded in real-world experience, you're in the right place. I publish new videos every week, so make sure you subscribe and stay connected. You will not want to miss what's coming next. Now it's time for me to introduce myself, right? My name is Jean-Joseph, and I am an independent consultant working at Tech Insight Group as a principal data and AI architect with over 2 decades of experience. I help teams design and build scalable, reliable analytic and AI solutions. I was at Microsoft working as a technical trainer, mainly focused on data, AI, and visualizations for over 3 years. I am also an MCT, which stands for Microsoft Certified Trainer, a speaker, blogger, and a data-driven community builder. You're probably asking yourself, for example, why Microsoft Fabric is the platform, okay, for this four-part machine learning lifecycle series. I know many of you are probably asking yourself such questions. Guess what? This question comes up all the time, and the answer is actually very straightforward. Okay, here are a clear reason Fabric stand out. The first one is that it gives you one unified platform. No more juggling 10 different tools like just to get one machine learning project out the door. Fabric brings data engineering, science, machine learning, real-time analytics, even Power BI into a single connected environment. Right? What would be the second reason? The second reason is that it's support the entire machine learning lifecycle end to end, right? From framing the problem to exploratory data analysis to training to batch scoring, everything lives in one place with shared governance and collaboration built in. It delivers enterprise-grade security and governance by default. So you get lineage, access control, compliance, and auditability without extra configurations. So your ML workflows are secure from day one. It's give you optimized Spark compute without the headaches. Fabric handles auto-scaling, job admissions, and resource-aware scheduling behind the scene. So your exploratory data analysis and training jobs run fast and predictably. The last point is that it makes operationalization simple and repeatable with pipelines, the model registry, the feature store and batch scoring built in, moving from experimentations to productions, become a clean, reliable process, not a science project, right? To really get the most out of each part of this four-part machine learning lifecycle series, let's get ground everything in a real business use case. Why? Because concepts make sense on paper, but they become so much clearer when you see how they solve an actual problem end to end. So, before we dive into the details, let's start with a scenario by bringing all of this together, right? Imagine you're a real estate company trying to predict properties value across different neighborhoods. You've got years of transaction data, demographic trends, and market indicators. But the question is, how do you turn all that data into actionable intelligence that drive business decisions? That's exactly where this four-part series comes in. It's not just about machine learning, it's about building a repeatable, business-aligned workflow that connect data strategy to measurable outcome using Microsoft Fabric, right? Here's the thing, there must be a starting point. Every successful machine learning project starts with clarity. We begin by defining the business problem, not the algorithm. It will be a mistake. In our real estate example, the goal isn't train a model. Instead, it's help investors identify undervalued properties. From there, we translate that into an analytical questions, understand what data is required, and define how the insight will be consumed, whether through dashboards, real-time endpoint, API, batch endpoint, or automated report. These steps ensure that every technical decisions align with business value. Things you need to take in considerations. Once the problem is framed, we dive into the data itself. Here, we explore patterns, detect anomalies, and prepare features that truly represent the business reality. In real estate, that might mean normalizing price per square foot, encoding location attributes, or handling missing data from older listing. This stage is where data scientists and engineers collaborate to make the data set trustworthy and usable. Now we bring the intelligence to life. We train models, we evaluate metrics, and iterate until performance meets business expectation. But it's not just about accuracy, it's about interpretability and reliability. In our example, the model must explain why certain properties are predicted to appreciate, not just that they will. So this is where machine learning engineer and data scientists refined the model to make it production ready. Finally, we operationalize batch scoring turns trained model into scalable prediction engine. In Microsoft Fabric, this means integrating with pipelines, registries, and feature stores so predictions can flow seamlessly into business system. For the real estate case, that could mean daily updates to a dashboard, showing predicted property values, enabling faster, smarter investment decisions. This series is a blueprint for success, a structured end-to-end approach that helps organizations move from data curiosity to data confidence. Whether you're a business leader defining strategy, a data professional building pipelines, or an ML engineer deploying models, these four parts show how to connect every steps of the machine learning lifecycle to real business impact. So when you watch this series, don't just think about models, think about outcome. Think about how your organization can use Microsoft Fabric to turn data into decisions and decisions into measurable results. Now that we have walked through each stage of the machine learning lifecycle, let's bring it all together. This right here, the full machine learning batch scoring pipeline in Microsoft Fabric, right? So is the final goal of our four-part series. Everything we cover from framing the problem to EDA and preprocessing to model training all the way to batch inference leads to this complete end-to-end blueprint. This is the workflow that turned a real business use case into a production-ready solutions inside Microsoft Fabric. And by the time you finish this series, you will not only understand each piece, you will know exactly how they connect to deliver real measurable impact. It took me quite some time to put all of this together, and I truly hope it brings you value. Now, I need your support. The best way to help me with this channel, right, is to subscribe, like the video, share it with someone who might benefit, and drop a comment to let me know what you think. Your engagement really helps me keep creating content like this. Have fun, and let's get started with part one. Thank you. What exactly, team, is machine learning? By the way, anytime when you think of machine learning, think of a branch of artificial intelligence that enables system to learn patterns from data and make decisions or predictions without being explicitly programmed. In this context, machine learning is not just about algorithmic. Keep that in mind. It's about building an end-to-end pipeline that transforms raw data into actionable insights, from framing the right problem to deploying model in productions. Machine learning combines data engineering, statistical modeling, and automation to deliver measurable business value. So your next question could be, why Fabric? Microsoft Fabric provides a unified analytics platform that simplifies the entire life cycle. It's integrate data integrations, preparations, and storage through one lake and lakehouse. It's also support experimentation and training with Microsoft Fabric notebooks and ML experiments, and enables seamless deployment and monitoring all within a single environment. Guess what? With that, Fabric allows us to eliminate silos, reduces complexity, and accelerate time to value for enterprise-grade machine learning solutions. Now, team, let's dive into the core strategy for building a successful machine learning pipeline. And guess what? It all starts with the most critical steps by defining the problem statement. Before diving into data or algorithmics, the most critical steps in any machine learning project is framing the problem correctly. This ensures that the solutions aligns with business objective and deliver actionable insight. Here's a quick structure approach because inside of, as you can see on the screen, framing the problem, right, which is the foundation of ML, there's so many things we have to take. The number one thing we have to take is defining the problem. So the first step and most crucial steps in any machine learning project is defining the problem clearly and precisely. Without a well-defined problem, even the most advanced models will fail to deliver meaningful results, right? So the steps is about understanding the business objective and translating it into a challenge that ML can solve. So therefore, in here, while you have all business stakeholder available, application owners, the developers, the data scientists and AI engineer, you need to ask measurable questions like what outcome are we trying to achieve? What, why does this matter to business? We need to know how will success be measured? A strong problem definition ensures alignment between stakeholders, clarify scope, and set the foundations for every decisions that follows data requirements, modeling approach, and deployment strategy. In short, get these steps right, and the rest of the life cycle become far more effective and efficient. Second, we have to turn the problem we just identified into analytical questions. So what do I mean by that? Once the business problem is defined, the next step is to translate it into an analytical questions that is specific, measurable, and actionable. So this question should clearly state what you want to predict or estimate and how success will be evaluated. Let's take a basic example here. For example, what can we think of? Can we predict the probability of a customer churning within the next 60 days? We can ask different measurable and actionable questions. For instance, what is the expected demand for products X in the next quarter? A well-formed analytical question ensures clarity for data requirements. Yes, modeling approach, even the evaluation matrix. It also guarantees that your machine learning solutions will produce insights that can directly influence business decisions, such as prioritizing retention, campaigns, or adjusting inventory level. We still have more to do in the context of problem framing. The third step is to understand the data requirement. So let's go back a little bit. After defining the problem and arriving at a clear analytical questions, the next steps is to understand the data needed to answer that questions or those questions effectively. This involves identifying the right data source, determining which features are relevant, and ensuring historical data is available for training and validations. Here, you still have a tons of valuable questions you might need to ask. The first question we may ask is, what data do we need to support? Or what data do we need to support these analytical questions? Where does this data reside? Is it in the databases? Does it come from APIs, sensors, or external sources? Is the data complete? How accurate is the data? How compliant is the data when it comes to governance requirements? So we have to be able to answer those questions. So these steps is crucial because the quality, quantity, and relevance of your data directly determine the success of your model. It also includes accessing data freshness, handling missing value, and identifying potential bias. Importantly, the nature of your data influences the type of machine learning approach you will use. For instance, if your data set contains label examples where you have the input and output, a problem and solutions, you will likely use supervised learning. If labels are absent, unsupervised learning techniques such as clustering may apply. Within supervised learning, the data type and target variable determine whether you need regressions, which is continuous values, or classifications where you will be dealing with categorical outcomes, right? By thoroughly analyzing the data landscape, you set the stage for effective feature engineering, model selections, and pipeline design. So this ensures that your machine learning solutions is not only technical sound, but also aligned with business objectives and operational constraints. The last part we have to think here is defining the consumption's experience. This is very, very critical. Why? Because after defining the problem, shaping the analytical question, and understanding the data, the next step is to design how prediction will actually be consumed. Very important. This includes choosing between real time or batch scoring, right? Planning the computer and storage resources needed for scalable performance, and determining how predictions will integrate into dashboards, applications, or automated workflows. We have to take all of this into consideration. Equally important is ensuring the user experience drives actions through clear thresholds, confidence score, and contextual insight. Addressing these elements early ensure your machine learning solutions is not only accurate, but also operational sounds, cost efficiency, and align with real business workflow once the problem framing stage is completed. Now, it's time to move into the real world development and implementations. This phase transforms strategy into action through a structured pipeline that include data ingestions and preparations, feature engineering, model selections, training, evaluations, deployment, and ongoing monitoring. Each step is crucial to building a scalable, reliable, and high-performing machine learning solutions. Let's go over each steps in the development and implementation strategy. The first one we have to think is data ingestions and preparations. That lay the foundation for every successful model. This stage focuses on collecting data from reliable sources, cleaning and normalizing it to remove inconsistencies, and unifying multiple data sets into a coherent structure. It also includes handling missing values, balancing efficiency through sampling, and ensuring the data set reflect the true business context. From there, key transformation make the data truly modeling ready. What do I mean by? So this includes encoding categorical variables. So algorithm can interpret non-numerical informations, scaling numerical features to ensure fair weighting across different ranges, and managing outliers so extreme value don't distort model behavior. It also involves standardizing data type to avoid downstream processing errors and ensure smooth integrations across tools. Guess what? Together, these steps create a data set that is clean, consistent, and structurally aligned with how machine learning algorithms learn, setting the stage for accurate, reliable, and scalable outcome. What would be our next steps? Our next steps focus on feature engineering if needed. What exactly is feature engineering? Right? It's a process that enhances the raw data so the model can learn deeper patterns that are not immediately visible. This includes creating new variable through feature extractions, reducing complexity with dimensionality reductions technique, and encoding complex data type like text or images into meaningful numerical representations. These transformations help the model focus on the most informative signals rather than noise or irrelevant details. Beyond technical transformations, feature engineering also incorporates domain knowledge, such as customer lifetime value or risk indicators. So to embed real business context directly into the data set. Scaling and normalizing engineered features ensure they align with algorithmic requirements, especially for gradient-based models. When done well, feature engineering significantly boosts accuracy, stability, and interpretability, often delivering more impact than switching to a different algorithm. What do we have next? Next is model algorithmic selections, right? This is where technical rigor meets strategy, decision making, right? The process begins with proper data splitting to prevent leakage. Okay, just keep that in mind. Followed by feature selection, performed only on the training set to identify the most influential variables. So from there, the choice of algorithm depend on the nature of the data and the type of prediction needed. Supervised model for labeled outcome, unsupervised technique for pattern discovery, and dimensionality reductions approaches when simplifying high-dimensional dataset. So deep learning architecture come into play when the problem demand more complex representations. A critical part of this stage is balancing predictive performance with interpretability. Highly complex model like deep neural network may offer superior accuracy, but can be difficult to explain in a regulated environment, if we want to be honest with ourselves. However, simpler models, such as linear regressions or decision tree, provide transparency and clearer reasoning, which can be essential for audit, compliance, and stakeholder trust. So making these trade-offs thoughtfully ensure the selected model align with both business goal and operational constraint. Next is training process. The training process is where your model actually learn using the prepared features and choosing algorithmic to uncover patterns, address internal parameters, and build a predictive understanding that can generalize to new data. So to keep this phase transparent and repeatable, your documentation should outline how parameters are optimized, how hyperparameters are tuned, and how you ensure the model is learning effectively rather than memorizing the training sets. Very important. A strong training workflow also includes safeguards and performance check. Techniques like early stopping, drop out, and regularizations help prevent overfitting. I'm pretty sure you were thinking of this. While distributed training or GPU accelerations support scalability for large data sets. Throughout the process, monitoring metrics such as loss curve, accuracy, and validation performance allow you to detect issue early and refine the model as needed. Together, these practice ensure the model is not only trained well, but also stable, scalable, and ready for real-world deployment. What do we have next? Evaluations and validations. Those ensure your model perform well on data it has never seen. giving you confidence that it can generalize beyond the training environment. So this stage focuses on selecting the right matrix for your problem type, applying cross validation to test stability across different splits, and benchmarking multiple models under consistent considerations. It's also where you refine hyperparameters to squeeze out additional performance without compromising reliability. A strong validation workflow goes beyond accuracy alone. It includes robustness checks on a whole out test set. I'm pretty sure you know that, right? Monitoring for bias or even drift, and confirming that the model behave consistently under real world conditions. By approaching evaluation systematically, you ensure the final model is accurate, dependable, and ready for production deployment. What do we have here? We have deployment. Deployment is the stage where your validated model become operational and start delivering real value. So this involves choosing the right delivery mode. Should we go with real-time inference for instant low latency predictions, or batch scoring for scheduled high volume processing? And integrating those predictions into business workflow through APIs, dashboards, or applications. It's also where you plan for performance and scale by allocating the right compute resources. Configuring auto-scaling and ensuring the system can handle production workload efficiently. A successful deployment also requires strong governance and reliability. So this includes implementing security control, meeting compliance requirements, and thoroughly testing latency, throughput, and stability before going live. We have to think of this. We also need to leverage ML apps practice at automations, right? Version control and continuous delivery, helping you maintain consistency and reduce operational risk. When combined with Microsoft Fabric's unified platform, these practices streamline development and ensure your model deliver accurate, timely prediction at scale. What do we have less? It's monitoring and maintenance. Monitoring and maintenance ensure your model continue to perform well long after deployment. So this phase focuses on detecting changes in data or behavior, let's put it this way, such as concepts drift or data drift, by tracking stability metrics and comparing predictions against real world outcome. It's also include validations, incoming data for quality issues, watching for schema changes, and ensuring the scoring pipeline remain healthy as business conditions evolve. Sustaining performance requires a combination of automations and governance. So this includes setting up alerts for performance job, triggering retraining workflows when drift thresholds are met, and maintaining detailed log for compliance and auditing by continuously evaluating accuracy, reliability, and fairness, because we have to bring responsible AI into considerations. So you keep the model aligned with real world conditions and ensure it remains trustworthy, compliant, and valuable over time. As you can see, those are the elements you have to take in considerations after you frame your problem. And problem framing should be the foundation, right? So, to conclude, the hardest part of machine learning life cycle isn't coding, right? It's framing the problem correctly. So this first phase ensure that every decisions from data strategy to model architecture is driven by business value and technical feasibility. By investing time here, you guarantee that the next step deliver measurable impact. So our focus will mainly be on what we call exploratory data analysis and pre-processing. So with that said, let me introduce you to part two, right? When it comes to Fabric machine learning life cycle, success strategy from start to finish. Guess what? Part two is all about exploratory data analysis and pre-processing, the stage where you stop guessing and start understanding the data that will ultimately drive your models. In part one, we identify and frame the right business solutions. Now, the question becomes, does the data actually support that problem? And how should it be shaped to answer it, right? This section walk you through the essential steps for inspecting structure, checking completeness, and uncovering distributions, detecting outliers, and validating relationship between features. Every analysis you perform here should tie directly back to the business question defined in part one. Because EDA is not just about profiling data, it's about confirming whether the data can solve the problem you set out to address, right? I'm pretty sure you agree with me. ADA is critical because most machine learning failure don't come from the model. They come from misunderstood or poorly prepared data. By visualizing, summarizing, and stress testing your data set early, you expose hidden issues like skewed distributions, missing values, inconsistent categories, or weak feature target relationship long before they break your pipeline. These foundations directly influence the quality of our feature, the stability of your model, and the reliability of your predictions. In short, part two ensures that every model decision you make later is grounded in evidence, aligned with the business objective, and built on data you truly understand. So, speaking of understanding, we can see choices involved. Okay, let me bring our notebooks, and the notebooks is available. You can download it from the descriptions. Okay, so is that what we are doing here? Okay, we are trying to download regressions housing CSV5. Okay, this is the location where it will be downloaded. Okay, so before we dive into analysis, let's get familiar with the data set we will be working with, right? And that must be our goal, right? So if we're looking at here, okay, you can see this is the path. That's the exact path we are passing here to read that data, right? Let me go over this a little bit. This regression housing CSV file contains residential property records used to predict home sales price based on based on a mix of property attributes and location details. It uh, it includes what we call city, neighbor, wood, beds, bath, and so on. We can clearly see also we have what we call the sales price. So therefore, we have question and answer because we have both variables into our data set. We are dealing with what we call supervised, right? So our goal at this stage is to simply understand how these variables behave, okay? How they are distributed, how clean they are, and how strongly they're related to price before we engineer features or build any models, right? So let's go over this script. What we're basically doing is that this is the location, this is the raw data, we passing inside of that data frame. We leverage in Spark what we want to do. We want to read that, okay? So we tell Spark, I want you to take in consideration the file has header. We also tell Apache Spark to guess the schema definitions, and we want Apache Spark to treat all NC cells as nullable, and we say this is the information. So now we get that view. Perfect. Let's go here. Because you can't analyze what you don't understand. So therefore, we have to rely on what we call point schema in order to reveal the true structure of your data before anything else. I'm pretty sure you agree with me, right? So we can see now we have a good sense of the schema definitions, the type of data we are dealing with for each features. Great. When a colon hides issue like extreme value, inconsistent ranges, or unexpected missingness, the best way to get insight about your data when it comes to statistical information is to rely on what we call summary. Within this summary is that because now we see the data, if they are missing record, if they are, for example, inconsistent information, we won't be able to get it. And the best way, one of the best way to extract those information is to rely on summary. By analyzing each feature, we can see we have missing informations. If we're looking at baths and square feet, it is, for example, um, 970, whereas for Nick Bold and City, it is 1,000. If we're looking at lot, a crest is 970 as well, whereas has garage or renovation is 100. Okay, so that's good. Perfect. So now in here, we also have information we get regarding related to median, standard deviations, and we have what we call RQR, and 20%, 50%, 70%, and max. So we can see the max record is Jacksonville. We'll go over that very soon for Nick Bold. And then we have what we call suburban, okay, and the mean is downtown. So therefore, there are some information we might need to revisit here. You will understand what I'm saying very, very uh, short. So now we still have to validate those information. So what we're doing here, we are explicitly, okay, checking for skewed features, missing value, or extreme outliers that can impact your model accuracy, fairness, and stability. Okay, so if we looking at here is that we importing functions and we collecting the entire color name. Okay, so we, for example, looked through each column. Okay, and then we leverage what we call a key statement to count number of null inside of the data. So if we're looking at here, we can see bath is 30, square feet is 30, whereas we have 0 for city and neighborhood, and lot acres we have 30. So therefore, this information is related to this. So here is that we have to clean that data. So therefore, there are work that need to be done. So now we need to find a way, okay, to fill in missing value. That's exactly this code is simply cleaning up 3 columns in the data set that were identified as a feature that have missing value. So what we first doing here is that we first uh, we we name the column we want to work with. Okay, then we first make sure these column are being treated as what we call numeric, so they can be used in calculations. Okay, then we look um, uh, at each column and figure out the median value, the middle value. So, which is a reliable number to use when filling missing data. And the good thing is, if, for example, a column has no valid number at all, it falls back to using what we call the median. or for example, the average value, right? If it's not able to do that, we fall back to what we call zero, which is the least result. And finally, if you pay close attention, what we're doing here is that we replace all missing value in those columns with the median or fallback. So the data set is complete and ready for modeling. So if we're looking at here, we do the same display to get the summary. We can see now the entire information is being cleaned. How cool is this? Right? So that's good. So now the data is clean. What we need to understand is the distributions. Why am I saying this thing? Sometimes price data varies widely across cities or neighborhoods, right? And without checking, you might accidentally compare market that behave completely differently. For example, one city might have extremely high prices with a wide spread, while another has tightly clustered, lower priced homes. If you don't catch these differences early, your model can become biased, unstable, or misinterpreted location-based pattern. So what this script is doing, as we can see on the screen, is that it is quickly surface those issues by calculating the median, right? You have the medians, okay, price, and also you have what we call the interquartile range. For each, we have that for city, okay, as we can see, and we also have that for what we call neighborhood. So the medians, as you can see here, okay, the medians, okay, shows the typical price, while the IQR price tells you how spread out or volatile prices are within each city. Let's put it this way, right? In a wide uh, RQR mean price vary a lot, often due to mixed property type or inconsistent market conditions. And same apply, for example, for neighborhood if we have to go. In here, we can clearly see Jacksonville happen to be the most expensive one when it comes to median. However, if we're looking at here, is that for Antiqua Tal range, it is completely different. It's not really the highest, right? So meaning if we have to think of Nick Borough, downtown happen to be the most or the highest median, and also it happens to be the highest interquartile range, confirming a premium diverse price market. So here's the thing, team. By combining the data this way, you can you can instantly see which locations are expensive, which are stable or volatile, and where outliers might distort your model. Don't worry, we will see the visual way very shortly. So to summarize, it helps you validate whether location truly influence price and ensure your analysis stays in line with the business problem you're trying to solve. Okay. And other things you have to understand is that here the focus would be finding robust outliers, right? Before training a model, you need to know whether your data set contains extreme outliers, value so unusually high or low that they can distort your model, inflate error matrix, or cause unstable predictions. For example, if a single property with a widely inflated square footage or an impossible number of bedroom can pull your model in the wrong directions. This issue often hide in the data unless you explicitly look for them. Otherwise, it's hard to get that. So what we're doing here is that this code, if we're looking at here, calculates your IQR range, right? So it is doing that for example, for key metrics like price, anything that is numerical, and any feature you think is valuable, you want to do such analysis. For example, for each column, what it's doing, it's calculating what we call Q1, which is 25%, right? And also what we call Q3, which is 75%, and the interquartile range. That's exactly what it's doing here, right? So using this, it's determine the lower and upper limits, where, for example, um, um, a normal value should fail. Anything below or above those limits is flagged as a potential outlier. As we can see here, we can see for log across, we have 58 outliers. For price, we have 60. For what we call square foot, we have 4, right? So by looking at these, we would like to get access to those records and share those with business people. Okay, so that script, for example, this is a snippet if you want the result to be by feature, but if you want all result to be under one data frame, this is what I'm doing right here, is that if you recall, for price we have 16, for log accuracy, if I'm not mistaken, we have 58. Let's confirm. Yeah, it is 58. And then for square feet we have 4. So we can see here, let's go with what we call price. If we go on price, so take a look right there, we have price. If we're looking at here, it's finished here. If we look for that number, you should see it must be 16. So this is the last one. As you can see, we have the 16 records that are identified as outliers. And we also have the 4 records that are identified as outliers for feature what we call square feet. For lot acres, we have the 58 records that we can share with business, analyze it, right? We can bring any well-known person or department within our organization to help us figure this out, or should we exclude them um, from the training data set? Perfect. So here's the thing. Also, before modeling, you need to understand whether your categorical feature are balanced or heavily skewed, right? Why am I saying this? If one city appear 10x more often than others, or if almost every home has a garage, your model may learn bias pattern or completely ignore minority categories. These issues are easy to miss unless you explicitly check the distributions of each category. This loop, for example, as we can see, is generate frequency tables for key categorical columns. What do we have here? We have what we call city, neighborhood, has garage, and also renovations. So what we're doing here is that for each column, okay, we count them. That's what we're doing here, because we want to know how many times each category appear, and also we sort them from most common to least common. So this instantly shows whether your categories are balanced, dominated by a few value, right? Or contain rare categories that may need special handling, like grouping, encoding categories, or filtering. So when we're looking at this, is that we going over this result across each features, we can see we don't really have extreme imbalance, right? We don't really have nowhere categories, and the data doesn't really have nulls or unexpected value. So therefore, no need for category grouping or smoothing, as you can see, right? So now, another things we have to take in consideration before we start with the modeling process is that you need to quickly confirm whether locations actually impact price, right? If we have to think of a summary tables, alone can't show you how price spread, where the outlier are, or whether some location have much higher variability than others. So without a visual check, you risk treating all cities and neighborhood as if they behave the same, right? So what we're doing here is which is kind of exactly what we just did above right here. Let's see if we can bring this back. If we're looking at here, is that we can clearly see that 60 is the most expensive price, right? And we have the IQR. And for downtown, we can see that for Nick Bow, downtown happened to be the most expensive for both, for the median, which is the actual value, and for the volatile, which is the IQR. So if we go back again one more time, what we're doing here is that Let's see if we can go back. What we're doing in this code is that, okay, so we select the column we want to analyze or feature. We have a sampling, we're using 0.2, and the seed is 7, and we convert that to what we call to pandas. Okay, so now we're setting up a figure, and we call the first figure, which is a price distribution by city. That's what we're doing here. And then we performing that same analysis equals the same features, but this time the focus is not on city. This time the focus is on neighborhood, right? And then the target variable is price, as you can see here. So now we want to do price distributions by neighborhood, right? So let's go over city. If we go back here, you can see Jacksonville is the most expensive city, right? And if we're looking at um, Allentown, it is the least expensive. And if we go back one more time to that table, you should see that it match. So therefore, that information is valid what we're seeing on the screen. So let's go back again. Am I correct here? So just give me one quick second. We'll get there. If we're looking at Arlington, Arlington is the most expensive one. It seems like I said Allentown, so sorry about that. It's Arlington. I think probably a minute ago. So you can see it is the least expensive. So now, even for downtown, which is the most expensive, Wuwo is the least expensive. And if we go back, we can clearly see those informations happen to be exactly what we were expecting. Jacksonville. Let's go by Nick Bold. By Nick Bold, we can see downtown is the most expensive one, and Wowo is the least expensive. So we can go, when you download this, you will be able to see all those details. So basically speaking, this chart compare how home price vary across cities. So you can instantly see which cities are more expensive, which one are more affordable, and where price volatility is higher. Tailor boxes and longer. For example, whisker mean the market in that city has a wider spread of price, right? Perfect. Great. We're almost there. Don't worry. So in supervised machine learning, relationship between features matter. If you don't understand how your numerical variables related to each other, and to the target. So you risk feeding the model weak signals. Very important. So hidden predictors or hidden multicollinearity that can hurt performance, right? Guess what? A fast visual way to see how everything connects is correlations heat map. A correlation heat maps give you an immediate intuitive snapshot of how strongly each numerical feature is related to the others, right? So what we're doing here is that we are calling our features, okay? And then from this one, we're creating a new data frame. Within that data frame, we're using the correlations, and then the method is PSON, okay? Within the PSON, we set the figure, and then we pointing that result. If we're looking at here, is that the red cells highlight strong positive relationship. So therefore, the closer they are to red, the more related they are. So let's see, we have square feet is red right here. Let's go down and see what, hold on, that was price. We can see another strong red here, which is what we call square feet. When we're looking at here, we can see price. So that correlations, because we have to understand how a location, okay, can impact price. Okay, the number of room can impact price. The number of bathroom can impact price. So that visual give us such insight, right? Which is a quick way to identify which features matter for predictions, which one overlap too much, and where potential modeling issue may arise. And sometimes we might even need to remove or combine them. So this is very, very important before you train your model. It's ideal to understand the data. And also, team, machine learning models can work directly with text-based categorical features like city or neighborhood. If you feed raw string data into a model, it won't understand them. and you risk losing important location-based predictive signal. So you need a clean numerical representation that preserve categorical meaning without introducing bias. So if we're looking at here is that this is the data set, our data set, which is the regression housing.csv. If you recall, we dumped that into a data frame, okay, and then we did have some, for example, missing value. We fixed that. So therefore, that's the data we are dealing. But we still have some work to do. If we're looking at for city, it is Grand Rapid, there's Denver. So those are texts during the training, we do not want to keep them, right? So therefore, we need a way to turn that into a numerical value where we will assign index ID to each one, right? So this is where one-hot encoding comes in. One-hot encoding convert each category into its own binary column, giving the model a clear numerical way to learn location patterns, right? So the code you are seeing below extract the categorical colon and encode them safely using what we call one-hot encoding and rebuild the full data set with the new indicator feature. As you can see here, so the column was city, so we have city and neighborhood, right? So now if we're looking at, we have these two, and then what we're doing here, we selecting this column, and then we're creating a new data frame there. So what we're doing here, we're using one-hot encoding, and we're handling error, and then we fit that into we fit that data frame into our one-hot encoder, okay, and then we also get the feature name out of it, okay. So now what we're doing here now is that we are assigning we are dropping the colon and reset the index, okay, and then now we're pointing the old number of colon the data set has and the new number of colon the data set has. If we're looking at here for now, you can see previously the data set was 10 colons. So now after the one-hot encoding, right, the data set happened to be more than 10. So now it is 21. And now if we're looking at the number, the bed is still there, the bath is still there, the what we call square foot is still there. However, if we scroll all the way to the right, you will see there is city Arlington, there is city Boston. So now there are no more text, there are numbers. That's exactly what one-hot encoding allow you to do. It allow you to convert each variable within a feature into an index ID, right? As you can see here, which is 1 or 0. Perfect. If you're looking at here, let me close this and simplify for what we call neighborhood. We have downtown, rural, and so on. So now when we're looking at that data team, we are not there yet. There's so much things that need to be done, right? Even though, for example, now we don't have text base, but there's still room for improvement because we do not want to train the model using that data, which is imbalanced. If we take for square feet is way bigger than what we call bath. So therefore, leaving it this way can completely impact performance during the training. The square feet might dominate the entire training. So to prevent that, we have to scale that data set. Okay, so what the target feature is price. Okay, and here is that we are using, if I'm not mistaken, this is a min max scaler we are using. Okay, and let me bring my glasses to read this. So what we're doing is that we're defining the features. The features are the variables that the machine will learn in order for the machine to do a predictions on same data, like price, what would be the price, okay? So for each column, if we're looking at here, we look through them and we make sure we have that data type is numerical, okay? And then what we're doing here is that we performing what we are normalizing that data. This is what we call feature scaling, okay? So now if we're looking at here, once we get the output, we still have 21 columns, but now the square feet is no more big number, as you can see here. So the data is more, for example, a line. So therefore, that information, once the model receive it during the training, it will be more balanced, and the model will be able to learn better from each features. So as we have, for example, a clean data set, because the previous data set is no more valid, what we would do is to save that. This is what we're doing. So we're defining the locations and we're calling it regression housing clean on the that CSV. Yes, this is for demo. We leave it CSV, but it would best to leave it to convert it or save it as a Parquet file, okay? So now if the directory doesn't exist, we will create that. And then, yeah, we use notebook util to save that and we print that data save. If we go back right here, you should see that we were able to get that information. So this is the clean one. That's the original files we were working with. And then if I go back right there and I click here, you can see that this is the clean data set. Perfect. So here's the thing. As you can see, we do not want to train the model under a data set where we do not understand the distribution of the data. As you can see, we were able to identify multiple records in terms of outliers, right? And outliers can significantly impact your model stability, right? And the intent here is to give you the mindset of steps you might need to take when it comes to EDA, which is we stand for exploratory data analysis, and also the processing part. Because if we didn't perform such advanced analysis, we will not be able to identify if there were nulls, and also we wouldn't be able to understand if there were outliers. And moreover, we wouldn't be able to understand how square feet have a very strong relationship with price. So now we have that data stored somewhere. Welcome back to the Microsoft Fabric Machine Learning Lifecycle series. You are now in part 3 of this 4-part journey, where we move data from preparations into the core of machine learning, model training and evaluations. So as you can see, this is our notebooks, right? If you recall, this is the data that we clean in part 2. If you recall, if I click here, we should get a folder called clean. And if I click on that folder, what you will see, this is the file. And take a look, that's the same locations, right? So what did we do in this file, right? First of all, we clean it, we normalize it, as you can see here, and then any category code data, we leverage one-hot encoding. So this is what we did, right? So, and we are reading that data and return it. We return in the schema definition of that data. Okay, perfect. So here's the thing. When your data is clean, right, and ready to go, it's really tempting to jump straight into picking your features and target variables. That would be a mistake. Why am I saying this? Here's the thing. If you do that before splitting the data set, you're already letting the test set influence your choices, even if you don't want that or you didn't mean to. Just looking at correlations or deciding which column seems useful can quickly leak information from data that's supposed to stay unseen. That end up giving you a model that looks better than it actually is. So that's why seasoned ML engineer, data scientists split the data set first. By isolating the test set up front, you guarantee that every decisions, feature selections, model choice, hyperparameter tuning, and evaluations is driven only by the training data set. This keep your test set truly untouched and ensure your final matrix reflect real world behavior rather than accidental leakage. Splitting early isn't just a formality. It is the guardrail that keep your model honest, right? What we are doing here is that here we are leveraging the uh, train test set. And if you pay close attention, we have a one line of code. That one line of code simply allow you to take your full data set and split it into two parts, which is the training and the test set. If we're looking at here, we only see the test set size, right? That's the only thing we see, right? But here's the thing, because we already reserve 30% of the data size for testing, so the remaining of 70% happen to be for the training sets. Okay, what would be the advantage we are getting here, right? 70-30 split give the model plenty of data to learn from while still keeping a meaningful chunk for evaluations. Everything comes with pros and cons. What would be the downside, right? So if your data set is small, 30% might leave too little for training, so which can weaken model performance. So therefore, it is our responsibility to not undermine the data set during this splitting. That's the reason why sometimes you may see it is 80-20, it is 85-15, right? You also have to take in consideration not to leave a small subset of the data for testing as well during the training. There's another parameter we are seeing, which is random state, right? So this set the seed for the random number generator. So the split is reproducible. What is the advantage here, right? Consider if we are in a debugging process or we are sharing results across team members, you and anyone else. You would like to get the exact same number. That's exactly that random state equal to zero allow you to do. Anytime when we run the training model, we will get the same subset of the data after the splitting when it comes to the training and the test set. But using a fixed seed mean you always training on the same subset. Sometimes using different seed, right, or variant seed help you understand how stable your model really is, right? If you are not troubleshooting, you are not debugging, you are not sharing results where you want to make sure we get the same output for training and testing in terms of parameters and so on. And guess what happened? Change it might be better, right? So once the data splitting is done, right, the next step is, for example, move to the feature and target selections. Why? Now that the data set is safely split into training and testing set, so we need to explicitly separate the input the model will learn from. Those input are what we call features, as you can see on the screen, right? And if you're looking at here, we define a column that have all the features. So therefore, that is what the model will learn from during the training. And also, we define the value that we are trying to predict. And the value name is what we call label colon, because now we can clearly see that we are dealing with a supervised machine learning, because in a supervised machine learning, both variables have to be present, the independent variables and the dependent variables, right? So if we're looking at here, this is where we are starting with the feature selections. So we define a variable, which is X trend and test trend. They hold only the feature column, giving the model, right, the structure signal it will use to learn patterns from, okay? But remember, we did define the label value, so we require a subset of the data for the label. The label is the value you want to predict, right? So that store just the target column. In our case, it is price. So the model knows what outcome to map those features to, right? So creating these four variables is essential because it clearly isolates the independent variables from the dependent one and keep the training and testing workflow consistent, leak-free, and ready for any scikey learn model that expect this exact structure. Perfect. So let's go over ML flow. That's great. Once the data is prepared, the train test plate is defined, and the feature and the target are cleanly separated. So the next step you would normally go is to bring ML flow into the workflow, right? At this stage, you're about to start training your models. So you will need to log metrics, compare ones, and add the rating. Guess what? Doing all of that without a tracking system quickly become messy and impossible to reproduce. ML Flow, okay, solve that by giving you a structured place to record every experiment, which parameters you use, which model performs best, what artifacts were generated, and how each one compared to the others, right? So in short, once your data pipeline is ready, MLflow become the backbone that keep your experimentations organized, traceable, and productions ready, right? So what we're doing here is that we're importing MLflow. That's the name of our experimentations. This Once we set this here, we're setting the experiment, that's become a container that will keep track matrix of all experimentations. Each one can be considered as an experiment. Okay. So now we change the gear and our focus is on selecting the type of algorithmic that will learn from your data. As you can see here, we are using what we call linear regressions, right? This choice isn't random, to be honest with you. It's grounded in everything we uncovered during the discovery call. If you recall, when we were looking at a way to identify the business problem we are trying to solve, right? That's why part one is very important because it set the grounding, right? So during the discovery call also, we were able to structure and source of the data and how the predictions will ultimately be consumed. In this case, predicting housing prices is a classical supervised regression problem with continuous numeric output, which naturally point us toward algorithmic like linear regressions. We can even think of what we call random forest regression. We can bring gradient boosting or even more complex advanced models depending on complexity. But before exploring alternative, it's okay, perfectly reasonable to start with a simple, interpretable baseline model. And that's exactly why we begin with linear regressions. So let's go over the code together. So what we're doing here, we're importing linear regressions. Let me put my glasses on. Form what we call the linear model, right? So if we're looking at here is that we're setting up what we call ML flow.autolog. What exactly this one allows us to do? So this one ensure that every parameters, matrix, and artifact generated during training is automatically captured for traceability, right? So you may notice we also have what we call ML flow.start run, right? This block of code open a new experiment one. If you recall, when we define the experiment name, I mentioned it is a container. So therefore, that name will allow you to monitor any run, and each one is an experiment. Therefore, we can use different data set. different parameter tunings under that same experiment name and compare them and pick the best model that meet our business problem. Okay? So now we instantiate the linear regressions, and then we feed that into our training data set. If you recall, we have that for both, for the feature and the target. So now we log the estimator as regressions for us to quickly identify what algorithm did we use for this training. As you can see here, we have the one ID. This will always be unique all the time. So therefore, if I want another experiment, it will be another name. Okay, so therefore the experiment name can have, let me bring this down for you to be able to see what I'm reading. If we're looking at here, the experiment name, that's a container. This can have a number of one ID or one name. Perfect. So now let's go back here. Let me bring this to your attention, right? When we're looking at the first part of code, at this point, we officially move data preparations into model training with MLflow tracking every steps so you can iterate confidently and transparently. Now, we shift the conversation towards something every seasons. ML engineer or data scientist knows. Technically speaking, you would almost rely on AutoML, whether your data set is raw, partially clean, or fully processed. AutoML is designed to explore a wide range of algorithms, tune hyperparameters, evaluate performance, and surface the best model with minimal manual interventions. It's efficient, systematic, and ideal for production grade workflow. But for this demo, the goal is different. I want to expose you to the data science and ML engineering mindset. So the discipline of testing algorithmic manually, understanding the behavior, and seeing how each model learn from your features. That's why we are explicitly training individual algorithmic one by one instead of letting AutoML handle everything behind the scene, right? So now, therefore, in a typical machine learning process, you would likely test multiple algorithms instead of relying on the first one, right? That's the reason why AutoML comes into the picture, right? Would be your rescue. So this time, instead of relying on linear regressions, we are relying on what we call decision tree. That's exactly what we can see here, right? Within the decisions tree, I already explained all of this. This will automatically log every parameters, every matrix, and so on. So this will set a new one instance for your experiment. But now we are using a parameter that called max depth, right? What exactly max depth allow you to do? So let's put it this way. When we training the models, there are two kind of parameters. They are learn parameters, okay, that will learn your underlying data pattern, and they are hyperparameters. Hyperparameters control the behavior of the training. Setting max depth to 5 tell the tree how many level it is allowed to grow. A deeper tree can memorize very complex pattern, including noise, while a shallow tree forces the model to generalize. So choosing a depth of 5 based on my understanding of the data is a balanced starting point. So deep enough to capture meaningful structure in the housing data, but not so deep that it overfits immediately. So in practice, you would tune this value through cross validations or let AutoML optimize it for you. But for this demo, we are intentionally exploring the model manually so you can see how each algorithm behave. Okay. When we execute this and we start the estimator, with the algorithmic name, we get a new one name and the same experiment name. As you can see, this is the first experiment name, and the first one name, that's the same experiment name, and this is the second one name and same experiment name. So here's the thing. Once you have trained multiple algorithms and log the result with MLflow, the next step is to actually compare the performance. And that's what exactly, for example, we about to calculate here, right? So what we're doing, we're getting the all experiment, okay? And then we dump that into this variable, we point this, right? And then from MLflow, we perform a search, okay? So once we perform a search, guess what? We order by start time, and we take the max result to what exactly that means is that we were doing the training. We know we run 2 experiments. So we just want to focus on the last 2 experiments we just executed. Okay, that's exactly what we're doing. So now we taking all the metrics that are relevant to us. What you can see, this is the output. So let me bring this. So therefore, we can see these 2 outputs are, for example, this, let me go back right there. So it seems like, yeah, perfect. If we're looking at here, we have access to the linear regressions and the decision tree. So for the training score for regression, we can see it doesn't work as expected, right? And however, for the linear regressions, the training score gives us better performance, right? And remember, when it comes to regressions, our goal is to minimize error. Let's see, for mean absolute error, let's see what happened. Not only linear regressions give us better training score, the number of error happen to be less. The closest to zero, the better, right? This is different compared to classifications. Classification, our goal is to boost accuracy. And in the context of regressions, our goal is to minimize error. So from there, we can clearly see that the linear regression, technically speaking, perform better, even at the training score and the um, mean absolute error. So those metrics allow us to see that. Here's the thing. This is a little bit simple. So through algorithmic, it's easy to do the comparisons, right? In a busy environment, we may have multiple. So therefore, we would like to present that in a diagram for us to quickly see, right? But for doing that diagram, we only focus on what we call the training score. Okay, for your information, you would, for example, focus also on more matrix, but for in real life. So for this demo, we only focus here. So we relying on matplot. We create a figure, and then we look through those, and we create a visual diagram, and we can see now the linear regressions work better. That's for code, right? However, Microsoft Fabric also provide that information to you, right? So if we're looking at here, this is the second one. If you recall, the second one, this is the first one. If we pay close attention, the training score is 0.89, right? And then the mean absolute error is 53. If we click on this one, you can see how the training score low here and how the number of error happen to be here. There's a way we could have optimized this, right? And then we can save that model if we want to, but if we're looking at here, we can have access to the model metadata if we want. But if I click here, oh, I can download it here. If I click here, I can even compare one if I want to. Let me go back here. Let's say view one. I can compare them. Consider if, for example, the training score, I can go back, click here. Okay. I can click on edit. I can say, give me this as a bar, and then say replace. You can see, I can quickly see for mean absolute error, this run or experiment work better. right? For the training score, if I need to understand which one worked better and I need this as a colon, I can replace this. I can see, okay, these work better. So you can see that this one within our experiment work better. There's so many things we can do. Those are available to us. But technically speaking, to share this result with a broader audience, we would likely rely on code. That would be part of our notebook, right? But if you want also to have that same visibility, accessibility to those metrics, Microsoft Fabric provide that as well to you. Perfect. So hopefully you get the point. So there's so much more we can talk here, but let's go back here to our notebooks. Okay. So now remember, this is where we are now. So now here's the thing, Tim. Here's the thing, right? Now that the linear regression evaluation matrix meet our business expectations, it makes perfect sense to shift gears and move into the next phase. And that next phase is what we call model regressions. So this is the point where experimentation ends and operationalizations begin. In Microsoft Fabric batch scoring ecosystem, a registered model become the what we call authoritative version control asset that every downstream pipeline, okay, scoring job and deployment process depend on. Right? Best practice is to avoid scoring directly from a notebook run. You should never rely on that. Instead, what you should do, you should promote the validated model into the registry so it can be governed, tracked, version, and safely consumed by engineering team and automated system. Okay, so that's exactly what Discovery is doing. So what we're doing, if you pay close attention, we extracting the experiment name, right? We're getting all the one fall under that experiment name. We session it here, and then we use this as descendant execution time, which is 2, okay? And then we take the index ID that happened to be 1. If we go back here, you will see that the index ID of this one is 1. This is 0. So this one is one that gave us exactly what we want, okay? And what we're doing here, we require that one ID to register, okay? So that's going to be your URL. So we are constructing it here, and then we leverage register, MLflow.register model. We provide the model URL, and then we give it a name, okay? And then we point those as output and the version. If you're looking at this, this is version 1. That's the model name. If we go back under what we call our workspace, and we go back one more, you will see this is the model name, right? Regression settings. So I can click on this one, right? Now, only I can click on it. If you remember, we have an estimator, and that estimator, we tag the algorithmic name. If I click here, you will see that the estimator truly show their algorithmic name. So therefore, we only registered what we call the linear regressions. Okay, so this is the schema, but there's more we can talk here. I do not want to spend time. There's so many things we can talk. In part 4, I will cover them after the registrations, what you need to think of, because the registration doesn't provide an endpoint. So if you're looking at here, we don't have any endpoint, right? So because we don't have any endpoint, if we come here, there's so many things we can think of, right? So for now, let's stop the video from here. Welcome back to the Fabric Machine Learning Lifecycle series. You are now in part 4 of this 4-part journey where we take everything built so far and move into the final stage, which is operationalizing your model through batch scoring and predictions. This is where your trained and validated model finally delivers real, actionable output for the business. As I mentioned, the last part of this 4 series will focus on batch scoring. Therefore, what exactly is batch scoring in Microsoft Fabric? And remember, the context was real estate. If you recall, we had a regression housing.csv file, right, which is related to real estate data. So in real estate, batch scoring is ideal when a brokerage or listing platform needs to generate updates, price, predictions for thousands of properties at once. For example, refreshing home value estimates every night based on new sales, market shift, or neighborhood trends. This isn't a real-time problem. It's a large-scale, recurring inference workload where consistency, governance, and cost-efficient compute matter for more than millisecond latency. Batch scoring ensures every property is evaluated with the same model versions, producing stable, comparable price insight that agent, sellers, or analysts can trust. Why Microsoft Fabric? Microsoft Fabric is the perfect platform for this because it unifies the entire workflow, data ingestions, feature engineering, model training, model registrations, and batch inference directly inside one lake. As an ML engineer, I don't have to move data ecosystem or stitch together fragile pipelines. Fabric's Spark runtime handles distributed storage at scale. The MFlow registry guarantee the correct model version is used, and the results land instantly in lakehouse table or Power BI models for business team. It's a clean, governed end-to-end environment built for exactly this kind of high-volume, production-grade ML workload. You know what? Enough talk. Let's put this into motions, right? So let's go to our notebooks. This is our notebooks, okay? If we're looking at here, this is the testing data set. So what do I mean by? Before we can run batch scoring, right, in Microsoft Fabric, we need a fresh or unseen data set, meaning data the model did not see during training or evaluations. This is exactly how ML is supposed to work. You train the model on historical, label data, and then use batch scoring to generate predictions on new properties that don't have a price yet. Right? So if you pay close attention, previously when we were doing data exploratory analysis, you may recall we did have price, and therefore we had 10 columns. Now, if you notice, we only have 9 columns. Why am I saying this? Because in productions, even with supervised machine learning, you typically won't have the target variable include, because the whole point is to predict something the business doesn't know yet, right? So like the current market value of a room that hasn't sold. In real estate, this makes perfect sense because your business entity naturally deal with data set of all size. Sometimes a few dozen listing, sometimes tens of thousands. So each containing the same core features like city, neighborhood, beds, baths, square feet, and so on, right? So now this is the data that the model haven't seen yet. If you recall, doing the data exploratory analysis, we treat all the nullable, all the empty value as null. Okay. So if you pay close attention, is that you could be surprised to see I have to go and clean the data again for the batch predictions pipeline. Oh yes, we have to do that. Your live production batch scoring requests need to be cleaned too. Every pre-processing steps you applied during training must be applied again during batch scoring. If we have to name a few, like data cleansing, casting numeric field, converting value to converting categorical value to numerical. We can even think of feature engineering, scaling, imputing missing value, all of it, right? The model expect the exact same structure and transformation it saw during training. Otherwise, the input won't match the schema it learned from. The only thing that should not be part of batch scoring pipeline in production should be the EDA, which stands for exploratory data analysis, because EDA is just exploratory work meant for understanding the data set, not transforming it. So in productions, we no longer exploring, we are operationalizing. So batch scoring is about taking new unseen data and running it through the same deterministic pre-processing pipeline. So the model receives clean, consistent, production-ready feature every time. Okay, so if we pay close attention, you will see that if you recall in part 2, there was some missing value for this column because this column were nullables because they were nullable, right? That's the reason why we treat all MC value as nullable, right? And then we force the model to guess the schema. If we're looking at here, the same transformation we did in part 2, we repeat it here. If you recall, we did convert those variables, right? We did that. And also, if you recall, is that I don't want to go back to the same script, but if you recall, when we were replacing the empty value, if if we couldn't get nothing, we fall back to the main value. And if main value doesn't help, we default that to 0.0. If you recall, all the transformations should be done. This is where we've replaced, for example, the any, and then we have a clean data set, if you recall, right? So that's the same script. But we are not done yet, right? Here's the thing. What we are seeing here is a categorical data. Oh, yeah. So we need to convert categorical value to numerical so the model can understand and learn from housing attributes like city, okay? Neighborhoods or property type, which cannot be processed in their, I would say, raw text data, because machine learning learn better with numbers, right? So therefore, this has to be converted. And what we did, for example, we're using one-hot encoding to do the conversion. So this is here we have 9 columns previously, or in part 2 it was 10. And now once we're done with the one-hot encoding, okay, so what happened? We're gonna have more columns. You can see now the original data set was 9 columns, and then the encoding happened to be 20 because we convert each categorical data into an index value, where 0 meaning this is not Denver, 1 mean this is Denver. For example, if we go back right here, what we will see is that this is Boston is 0, Boston is 0, Boston is 0. Okay. If we're looking at Grand Rapids, is 1. So therefore, this is that means Grand Rapids is the city. And same apply, for example, for neighborhood. If we go back to the neighborhood, you will see for neighborhood, we have what we call downtown, which is 1. If you recall, for Grand Rapids, downtown is 1. So therefore, such transformation has to be done. But when we're looking at the data also, we can see the data is not balanced. So we need to scale that data. So what do I mean by that, right? Scaling numerical feature is very great. Why? Because it ensures that all housing attributes, like, for example, if we have a square feet here, for a build here, and what other example that I can take? Even lot acres, you can see those numbers are very, very huge. And whereas others, if you have to see the number of beds, sometimes they are 2 or 1, right? So we want those to be proportionally, okay, even, right? So that the what do I mean? We want those to contribute proportionally to the model instead of letting large range variables dominate the learning process. So with that said, it is not really best practice to train the model like that. Otherwise, whichever features happen to be the biggest might dominate the training. So this is what we're doing here. We're using a standard scaler, okay, and then this is the same code. We already explained those code. If you need more details about the code, I highly suggest you to watch part 2. Okay, now you can see that we have the value difference. So if you're looking at the square feet, it's no more 18, 13. So now it's more balanced across each features. The only thing we didn't scale were, for example, the one-hot encoding value, because you will be dealing with 1 or 0, which is binary. So there's no need to do that. But anything else, we did our best to, for example, scale them. Perfect. Great. If you recall, in part 3, we registered the model, right? And in order to actually leverage it in productions, we now need to fetch that registered version from ML Flow registry, right? So that's exactly the script is doing. So batch storage should never rely on a local model file or on in-memory objects. It must use a version validated model that has been formally tracked, approved, and stored. Okay, by loading the model directly from the registry, we guarantee that every scoring one use the exact same model version that was trained, evaluated, and promoted in part 3, right? Therefore, this gives us consistency, reproducibility, and full lineage when generating predictions on new on-scene housing data. Perfect. That's exactly what we're technically doing. If we're looking at here, this is the name of our model, right? If I go back right here, just give me a second, and I go over Power BI, if it's allowing me to do that, not to authenticate. So hopefully it is enough. Okay. So now you may notice if we go and look at our workspace, you will see we have a model that called, okay, regression selling housing. You can see the type is ML model. This is exactly the model we are calling here. And we need the version, which is 0. If we click on it, okay, we should see the version is 0 because I created this model, this workspace yesterday, no, this week, okay, over the weekend, okay. So just to make sure everything gets started from scratch. So as you can see here, perfect. So now, in order for us to load it, we need a URI, right? So this is the name and the version. So after models, we require the model name and the version. We point out the URI, and then we call MLflow by function, and we load that model. So once the model is loaded, technically speaking, it's always the best practices to include the signature, because the signature is like a stamp you put to tell the model these are the expected schema definitions. So we didn't add that because I wanted the video to be a little bit short. But once you load that, technically speaking, you are ready to take advantage of batch scoring in Microsoft Fabric. However, you need to understand that, right? You require validating and alignment input feature. So what do I mean by that? Is that um, when your batch scoring data set doesn't perfectly match the model expected input, one colon, missing field, or even a different order, right? The model can't score reliably and may fail outright. What would be the solutions team? The model signature act as the contract that's define exactly which features the model expect. By validating and aligning our incoming data set to that signature, we ensure the model receive the same structure it was trained on to keep batch scoring consistent, predictable, and safer for production use. So that's exactly what we're doing here. If you recall, so this is our model. We import MLflow, but we didn't need that. We have that here, but we just have that. But those are the features, right? That's the features. You see that features come from this data set. If you recall, when we fix the data, just give you 1 second. Where is the data? So that's the data that's with, why is it? Just give me 1 second. The last one we did, was this one. Perfect. Yeah, this is the one that have the scale. Perfect. So if we're looking at here, team, okay, we get all the features, right? And then we have the model URI right there. Okay, we reuse it, okay? And then we check for the signature. If there is any signature, we would like to bring that back. But if we go back here, because we didn't explicitly mention it, you will get what we call a tensor data type. And if we go over the ML model, you will see the signature for the input signature. So that's going to be the feature, the schema definitions for each features, okay? So meaning for each feature, you require the name and the data type. And the output would be the predicted value. So that in our case, that would be price, okay? So now if we're looking at here, and those same information there, not only you have the model UUID, you also have the one ID in case if you did execute multiple run on leveraging different hyperparameter tuning or different validation test set. So if you want to make sure which one was the last one you happen to register as your model, so all of this information can be found here, to be honest with you, okay? So perfect. So now here's the thing, Tim. If you here, I will speak a little bit, okay, but I would highly suggest you to rely on Copilot to have Copilot explain it. Let me focus on what we call the mindset, right? So let's see. Perfect. After generating predictions, Tim, the raw model output really lined up cleanly with your original data set, right? And the best way or the way that I have seen ML apps engineer handle that is rely on index. Because why? Indexes may be off, right? Because we clean that data, we scale that data, we perform one hot encoding. So we don't have the same underlying data set, right? So prediction area may come in different shapes. It doesn't matter if we are dealing with regressions, classification, or probability. And the results are often not human readable. How could we read these informations? It's hard to read it. Those are the language the model talk. We do not understand that, right? So during the predictions, we do not want to return that information to our business users, right? So those are the things. This is what we are calling. That's the reason why we want it to be human readable, right? So why? Because for example, if you don't want it to be human readable, it's going to be hard for people to understand your result, even though the prediction happened to be accurate. And guess what happened? This one is exactly working to make the alignment using an index. If you're looking at here, is that the first thing we are doing here is, for example, just give me a second, we are defining the functions here. We first we set the index, we're defining a function here, okay? So perfect. And then what we're doing here is that we performing a tons of detections. We want to know if it's regressions, what would be the task? Is it classifications, okay? Or is it probabilities? Or is it a task that we do not know? And then what we're doing here is that we're trying to predict and map out the index. That's exactly what we do. If I have to summarize it, is that this code detects the prediction type format value appropriately, right? That's exactly what it's doing in order for us to make sure the information is readable. This is where we're performing what we call the predictions. The predictions mean, if I select this one, you will see that it is, for example, is first grab our DF scale features, it make a copy, and then it goes and reset what we call the index. That's what. And then it's drop it as well, okay? So now this is where the alignment done. And then that alignment, we concatenate this and we give it in a way that we will be able to do a predictions. However, doing the predictions, we may require a different format. The information, we might need it to be, for example, let me show you something. We might need it to be formatted in a different way. Like this is the score predictions, right? And this is the score predictions readable. But both of them, they're not we do not have too much change here. However, we can still add the dollar sign. I think I have a code below to do that. But for now, let's focus on this one. If we're looking at here, after we're done, for example, this is what allows us to perform the batch scoring. So technically speaking, let's put it this way. The model that we load, if you recall, we pass the feature data set into that model, and that model gives us the raw data, and we pass that raw data into these functions that we created, right? If you're looking at the raw prep data is one of the, for example, input parameter, then we work our way, we define the task. In our case, it is regressions, okay? And then we make the predictions, okay? So now, if we're looking at here, we were able to get that result set. Now that result set is considered if I need Grand Rapids City and I want to know the price, right? So if we go back here, it's in, hopefully, this is what we have. We have 2 beds, 1 room, that's the square feet, okay? So we do not have price right here. So we need the price here now. So now if we pay close attention, okay, let me show you this. You will see that we have 2 beds. We have 1 bath, we have the square feet, that's the here. So that's exactly the same data we are getting. So if we're looking at here, we get the price. That's going to be the price. So that's good, Sim. So now here's the thing. Let's come here, Sim. What we're going to do here is that I'm importing call functions from functions, okay? And now this is the data set. That's the original data set that I'm trying to filter. So I need Grand City Rapid is equal to 1.0. Okay, if we go back, that's the first line we are looking for. If I come back here, we go under city. Let's see, this is the city, the Grand Rapids, that's one. And then we want the neighborhood to be downtown. Okay, so if we go back here for that same column, let's go over neighborhood, we have downtown, which is 1 as well. So if we go back for beds, we require beds to be 2. So let's go back here, we have 2 beds, okay? And we also require here to be 1978. So if you pay close attention, this is 1978. That's the same information. So we want the square foot to be 1813. So if we're looking at here, it is 1813. When we're looking at these informations, so as you can see, that's the information we have, right? So we even add the dollar sign. In your case, it might be different. It could be pound, euro, and so on, or good, which for Haitian, because you know I'm Haitian. So that could be anything, right, in terms of the monetary sign, okay? So, so now what we would do, we would like to match that record. Okay? We want to match that record to the existing information that we have before, to a house that was sold that have kind of the same feature to see if the price will match, right? So if we're looking at, we got 2 records from that data. So the first one is that everything match. If you're looking at the here, everything match here. But the price is 74. However, this one, just give me 1 second, the price is 73. So you can see the prediction is not that off, but our goal is to minimize error when we're dealing with regressions. So we will normally have a threshold. In order for us to sell that house, it has to be within that range. So consider the range could be 70 to 75. So in our case, if we set that range, we are still inside of that range and we can still take off a profit as well. So therefore, it is ideal to understand that. So if we're looking at here, it meets our expectations. So if we want to try Jacksonville, for example, if we go, let's focus on the result. Okay, so for Jacksonville, so if we're looking at here now, Jacksonville will be 1. Just give me 1 second. We will look at that's Boston. That this is where is Jacksonville. It's interesting. I cannot see it right here, so hopefully I did not pass it already. So Jackson. Okay, perfect. This is Jackson. Jacksonville happened to be one. Okay, so that's what we have. And we need downtown has to be one as well. We have downtown. Let's go to neighborhood. We have downtown for neighborhood. That's one. Okay, beds is two. Let's go back to beds. We have two. And then here is 1985. We have 1985. And then the square feet is 2479. We have that. So that's going to be the price. If we go back to our data set, where we have a similar house that was sold, and then we can take a look and see the information happened to be kind of the same, but the price is not totally the same. This is 12, if you recall, and then these predictions is, I think, if I'm not mistaken, 10. If you're looking at here, it's like here, and we'll normally have a range again. The range could be between 10 to 15. So therefore, if it's 12, it still falls under the range because remember, the goal is to minimize what we call anyway, so this is a simple way we could have bring the dollar sign or your own country monetary sign. Okay, let's not spend time here. Let's go back on things that really matter because these are the things where not only you were able to do the batch predictions, but the result is valuable to human. So what do I mean by is that if you want to turn model prediction into something human readable, you first need a reliable way to match each prediction back to the exact where it came from, if you recall, with the terms of transformation. But if you remember, in part two, we transform the data heavily. We leverage one-hot encoding, scaling, and other pre-processing steps. Even within this batch, we still have to do that, right? All of that can shovel or reshape the data set. And without a stable identifier, so you lose the ability to reconnect predictions to the original world, right? That's the reason why you may notice we define what we call we import a Windows. Within that Windows, we have we're generating a world ID, okay, and then in here we adding a colon. We call that colon world ID, and then we're generating the colon over our Windows that we generate here. So therefore, that give us a whole ID for us to look through and get that information. So technically speaking, this code creates, for example, a stable whole ID in Spark before converting to pandas, right? So that whole ID act like a permanent tag for each record, surviving all downstream transformations. When predictions are generated later, you can merge them cleanly back into the original human readable data set with perfect alignment if we have to think of. Great. So what this code is doing right here, for example, here, what we are trying to do is that we are trying to preserve row and identify each rows that come from the raw data set with the role that has been changed during the one-hot encoding scaling. So to speak the machine learning language, we have to transform our data, right? What do I mean that? Like one-hot encoding, scaling, imputing, expanding colon, and reshape everything so the model can learn, right? That's perfect for training and scoring. But once the model produces predictions, our priority shift, right? So humans don't think in one heart vector or scale numeric ranges, right? So they need plain readable text that reflects the original category and values. So that's exactly, for example, what this code is doing. What exactly this code is doing is that it's create and preserve a deterministic word ID in Spark before moving into Pandas. So that YID you saw previously is exactly what it's doing. So it's kind of evident. This is where I just show you what we can do. So if we see here, for example, you see that YID, we look to that YID if it's not part of that column, right? So what we're doing, we add that we assign the ID this value, as you can see here, okay? So now what we're doing here, this is just for the US dollar. We're performing search predictions, okay? We're using the lambda functions, and then we're creating a data frame out of that information along with the word ID, okay? So now that's going to be the data frame imputed scored. So in that one, what we're doing is that we're joining this data frame that has the ID with this data frame, okay? And we rely on the word ID, but of course we're performing a left join, right? This is optional, but I just add it, okay? And display. So now if we pay close attention, the entire information is human readable. How cool is this? So we are no more dealing with one hot encoding and scaling. So what we are seeing, city is Grand Rapids, Nick Bold is downtown, and we have two beds, one bathroom and this square. This is the exact same record we were going over to look at the predictions. So look at now we can get that information. So now anyone can come and enjoy it instead of, for example, talk the language only the model understand, which is what we call if we're looking at here, even though if we bring this information, so here is city one, let me go, this is for Grand Rapid, this is downtown, where is downtown one. So now those information are useless when it comes to business user. So even though we bring a little bit of the plain text that human can understand, but the best way to make it readable is to create some extra code where we bring the entire data set. So if we're looking at here, that should be 10 columns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because our goal is to predict the number, the price. So this is the data set we started early. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. This one doesn't have pricing. So we use this data set, okay? We clean it, we pre-process it, and then we type that into our predictions, our batch scoring, okay? This is where we load it, that's the data, okay? Those are the 9 features that are here. The model, we load it. If you recall, we load the model from here, right? So that model is what we are using here to do the batch scoring. So that model is what we use kind of a couple code to map the predictions to the correct rows, okay? So now that our batch scoring pipeline has produced predictions and they are available in the data frame, the next logical steps is to publish this result into a lake table, as you can see, because the data is still inside of the data frame, right? That's exactly what this snippet does. What it's doing, it takes that data frame, write it into a table, right? And override the existing one. This is kind of job and create or truncate load. However, in production, this could be appended, okay? And also, what you might be thinking is, why do we need to do this, right? So the reason why we turn those predictions into a doable governed asset is that we want that if data to be available to the rest of the platform. Okay, so therefore, what do I mean by once the data is stored? This way, Spark, SQL, and Power BI can all query it directly. No extra pipeline, no duplicated data because of the one day. Just one clean source that monitoring jobs and retraining workflows can tap into without any additional works. Right, just keep that in mind. What we're doing here, we're verifying that this table has the record. We're pointing the top 20%. Okay, so now that information is stored for downstream processes, right? So this is a SQL we're using as well because the same way we rely on Spark, as you can see here, we can also rely on SQL, right? And we were able to query that data. Perfect. And if we go back to our workspace, and then we go back to our data lake, you will see that table there. So let's wait until the loading is done. So this is the table we have now. Take a look. We can, for example, rename it here. We can see where the files are located. We can perform maintenance, or we can open this in a new tab. So therefore, this is queryable, to be honest with you. And Power BI can use it. And any SQL endpoint when it comes to lakehouse or the data warehouse can take advantage of this. And that can be part of your data pipeline as well. Great. There is another advantage you get. What is it? The other advantage is that by storing the predictions as a formal table, we can apply fine-grained governance from day one, specifically when it comes to row-level security that allow us to control who can search with slices of the data, while column-level security protects sensitive attributes such as, I would say, pricing or identifier we just predicted. Great. So if we pay attention, we can see that there is a manage one lake security. Therefore, manage one lake security is one of the places that you can go and search fine-grained governance from day one. Okay, if we click on it, now okay, so it has to take a second. So I can go and create a new role. So this is how I can create that role. If I want, I can, for example, provide read write and read write if I want to. I can also select the specific data that I want. Okay, consider in here I have 2 tables, but the security that I need to apply has to be under this table. I can add that table. I can come give it a name. Let's call it this YouTube video. Okay, let's call it this YouTube video. So now here I can look for the username, but in production, you would likely go with a security group. For this demo, we will rely on a username. I can click here. Yeah, I can add members, which is kind of the same thing. If I want to come here, I can go and add members if I want to. So now what you can see here is a preview of the data, right? So we granted it access. We can create that wall. Once this wall is created, okay, so once it is created, this is the wall. I can click on it. I can click on edit permissions as well. I can apply security wall if I want to. If I click on security wall, what you will see, it's give me access to add the query. You can see this is the table we have where. So consider if you are providing services to multiple different real estate services where each one manage one or more city. So therefore, we can break it down by city. And same apply for the predicted value, which is price. If we do not want anyone to access that, we can come create a new rule or enable colon level security. This will get you the same thing. If we're looking at price, this is the predicted value, right? I can select this and enable colon level security. This is the one that have a defensive format where we bring the dollar sign. So consider if you're Haitian, like I am, okay, it would be good, right? This can be anything. It could be pound, it could be euro, and so on, right? So once this is done, all you have to do, for some reason, I'm not able to see the options where I have to say create or save, okay? But technically speaking, you have my work, okay? Perfect. So now let's discard this. Great. So there is another advantage we get also, team, right? By storing this table in the lakehouse, we are not just saving data, we are turning it into a governed asset that can move through environments the same way any other production resources does. A workspace can be wired into a CI/CD pipeline, so the table definition, permissions, and updates are all deployed constantly across dev, test, and productions without manual fix or one-off configurations. So the focus is more like batch scoring, but in case if you want to make this workspace to be part of the deployment pipeline, this is options that is available to you. If I click here, I can go create different kind of environment based on my organization standard. Okay.